All right, so now let's talk about the Newton-Cotes formula for n equals to 2. Okay, so as you recall, the basic idea behind the Newton-Cotes formula is that you're going to try to, given a function f of x, right, I'm going to approximate with some polynomial, some interpolating polynomial, in this case p2 of x, which is a quadratic polynomial with the property that p2 at three equally spaced points agrees with f of x, which is of course what is meant by p2 being an interpolating polynomial for x. So okay, let's say f of a, and then p2 at the midpoint a plus b over 2 is f of a plus b over 2, and then p2 at b is equal to f at b. Okay, so the picture to keep in mind is that you have some interval from a to b and a midpoint a plus b over 2. You have some function values, right, and you look at an interpolating polynomial which goes through those points, okay, which is of the of sort of quadratic degree, basically, right, degree 2. And then what you're going to do is you're going to approximate the integral, it's like f of x over the interval from a to b by the exact integral of this interpolating polynomial. Okay, so so we're going to have that the integral from a to b of f of x dx, right, is approximately equal to an integral from a to b of p2 of x dx. And I can write down an expression for that interpolating polynomial, right, in Lagrange form. Okay, so that's the integral from a to b of f at a times the Lagrange polynomial associated with that, which, if you recall, it's like has value. So the Lagrange polynomial associated with point A has value 1 at A and 0 at the other 2 points. Okay, so if it has 0 at the other 2 points, you know that it is the product of two linear factors, one with a root at x plus b, so a plus b over 2, and the other one with a root at b. Okay, so that's x minus a plus b over 2 and x minus b. And in addition to that, that Lagrange polynomial evaluates to 1 at the point A, so I can normalize this by the value at A in order to guarantee that indeed it takes value 1 at those points, at the point A. Okay, so you can check easily that this polynomial has the desired property that it vanishes at a plus b over 2 and at b, and at the point A it evaluates to 1. Okay, so that's the FA term. I can keep doing this for the f at a plus b over 2 term. And then you have x minus, so now this term has to vanish at a and b and evaluate to 1 at the midpoint a plus b over 2. Okay, so a plus b over 2 minus a plus b over 2 minus b. So again, you can convince yourself easily that it vanishes at a and at b, and at the point a plus b over 2, this evaluates to 1 because I've normalized the numerator by the denominator. Okay. All right, so you have the same thing for fb. Right now it has to vanish at a and a plus b over 2. And it has to evaluate to 1 at b. Okay. Okay, so the sort of the procedure, right, hopefully that's sort of sunk in by now. But again, the main procedure is to realize, well, what things have to vanish, right, at which points it's like this polynomial has to vanish, which gives you the linear factors in the numerator. And then you also sort of know that at the other point, at the distinguished point, it has to evaluate to 1. So you divide this polynomial, this quadratic polynomial, more generally polynomial degree n, by the evaluation of that at the point where it should be 1. So you divide it by this, and of course, when you happen to evaluate this polynomial at a, right, you substitute x equals to a, and then the numerator is exactly equal to the denominator, so it evaluates to 1. Okay, so this is what ends up happening, all right? So that's replacing, that's just this thing in the square brackets is really just the expression for this P2, which is this Lagrange interpolating polynomial of degree 2. Okay, and then what you can observe is that these FAs, FA plus B over 2s, and FBs, it's like are independent of x, so I can take them out of the integral, okay? And then what ends up happening then is that I get f of a integral from a to b of x minus a plus b over 2. I'll just write this down. Sorry, that's a plus b over 2. Okay. Okay, all right, and then this deferred term, it's like okay, and then I'm going to call these coefficients a1, a2, and a3. Right, which then allows me to say that this integral is approximated by a1 f of a plus a2 f of a plus b over 2 and a3 f of b. Okay, all right. So let's make some observations about this. All right, so I'm going to erase it's like this part here and just leave these two lost expressions. And then I'll make some observations. All right, so this, right, is an approximation of the integral from a to b of f of x dx. All right. Okay, so the first remark is the following. So you know that by the properties of interpolating polynomials of degree n are exact for polynomials up to degree n. And what I mean by that is that if f of x happens to be a polynomial of degree 2 in this case, of up to degree 2, which means that it's either a constant function, a linear function, or quadratic function in x, right, then when you replace it with p2 of x, right, this Newton interpolating polynomial, p2 of x is going to be exactly equal to f of x. And the reason for this is basically because if you look at the difference between p2 of x and f of x, at the points x0, x1, and x2, they all vanish. Okay, so the difference vanishes, and the difference between p2 of x and f of x, if f of x happens to be a quadratic polynomial, right, is also a quadratic polynomial. And so if you have a quadratic polynomial with 3 distinct roots, it has to be identically 0. Okay, and that's sort of more generally true. It's like, if you recall, it's like when you were first introduced to interpolating polynomials. So in any case, the first remark is that if f of x is in polynomials up to degree 2 in x, right, then f of x is actually identically equal to p2 of x, right? And so the Newton-Cotes formula is exact. Okay, all right, so let's sort of look at the converse, right? Say I know that this formula integral from a to b of f of x dx, right, which is, I write it as being approximated by a1 f at a plus a2 f at a plus b over 2 and a3 f of b, right, is exact for quadratic polynomials, right? What can I say about it? Right, so what can I conclude? Okay. so what I can do, of course, is that I can I can check that AI is going to be the integral from a to b of this Lagrange polynomial of degree 2. It's like at the point I, okay, x dx. Okay. All right. So where L2I is of x is the Lagrange interpolating polynomial, right? Well, the Lagrange polynomials. Okay. And how do I know that? I know this because I let, let's say, f of x be one of the Lagrange polynomials. So let's say L2I of x dx, sorry, L2I of x. Okay. So I have the integral from a to b of f of x dx, right, is equal to the integral from a to b of L2I of x dx. Okay. All right, and then I substitute this formula. So this is going to be equal to a1 f at a plus a2. Well, sorry, it's not f, right? a1 L2 L20 at a. Well, actually, okay, so maybe let me just change the notation a bit. I'll just call this L20 at x0, right? So x0 is equal to a, x1 is equal to a plus b over 2, and x2 is equal to b. Okay, plus 8. Okay, again, maybe the notation is better off. Sorry, let me change the notation slightly. Let's call that a0, a1, and a2. All right, and then this is a0, a1, and a2. Okay, so with that notation, right, this becomes a0 L20, it's like at x0 plus a1 L21 at x1 plus a2 L22 at x2. Okay, sorry, no, that's not what I wanted to do, right? They all should be Li. Okay, my bad. Okay, so so I'm evaluating the okay, so what I'm doing is I'm writing down, it's like this Lagrange polynomial, right, which is quadratic, right? And I said that the formula is exact for quadratic functions, so this integral is exactly equal to this thing, okay? But see, when you have L2I x0, it's like L2I x1 and L2I x2, all those things vanish except at the point xi, right? So so this is going to be just equal to a sub I, okay, right, for any I. Okay, so so that's telling you then that AI is equal to this integral from a to b of L2I x dx, which is exactly what I had claimed, right? So this was the claim that if you know that you have a approximation of the integral by this linear combination of the function values at these 3 points, and you in addition know that that formula is exact for quadratic polynomials, then you're forced to conclude that those coefficients, so let me again write these coefficients in my reindexed form, a0, a1, a2, you know that those coefficients, it's like have to be exactly related to the integral of these Lagrange polynomials. Okay, so it sort of goes both ways. On the one hand, you can start with this point of view that I take a function, I replace it with a polynomial interpolant, and I exactly evaluate that. That gives you a formula, and you know from properties of interpolating polynomials that this formula will be exact for quadratic polynomials, right? So if f is a quadratic polynomial or a linear polynomial or just the constants, this would be exact. Conversely, if I know that if I try to approximate f of x again by this linear combination, and I tell you that that formula is exact for up to quadratic polynomials, then it has to be that those coefficients are given by these integrals of the corresponding Lagrange polynomials. So that's sort of an if and only if statement. Okay, so so with this in mind, with this second point of view in mind, right, that's going to allow you to compute these coefficients in a slightly different way by essentially evaluating integrals exactly for for some basis, it's like of the polynomials, and then trying to figure out what these coefficients are. It's like by some sort of linear system of equations, instead of having to exactly evaluate these Lagrange polynomials. So, and the reason, of course, is that as you can sort of easily see, right, as you go to higher and higher degree in the interpolating polynomial, these expressions can be quite complicated and might not be so pleasant to integrate. Okay, so let me just stop here for now, and then we'll next talk about the method of undetermined coefficients.